Well, thank you all for coming out this evening. It is a treat for me to be here for so many reasons, because this area is so gorgeous, especially this time of year when some of the rest of us are buried in fact, just 4 days ago, I had been out without power for an entire week in my house. It's good to be here. And I also have to say what a treat it's been to meet Mary Smart and to have her hosting this event. And so I'm glad to be here. What I'm going to tell you about is, we'll go back to the slide, are some really fundamental studies. They are very basic studies of water. But I hope that I get across to you the concept that even though water is around us every day and we drink it and we bathe in it and we play in it, there's an awful lot we don't know about water. And that's particularly as it relates to environmental processes. And as we have large changes in the climate and variation, we're going to be changing a lot of the chemistry that happens up in the environment, in the atmosphere. And a lot of the chemistry that happens up there has to do with water. And so what I'm going to do today, I'll tell you some very fundamental studies that my laboratory and I have been doing for a number of years in this area. And so I certainly welcome your questions as we go through this, and I guess towards the end. So surf, sink, or swim, the title is because that really captures what we try to understand at a water surface, because it's the interaction of a water surface with a lot of things in the environment that controls a lot of the things on this planet. And so we'll start out first talking a little bit about the properties of water and maybe remind you of a little bit of the chemistry you might have forgotten or you know about water itself, and then we'll go on to talk about water surfaces. So water, it's pretty simple, but also just incredibly complex for this triatomic molecule with its oxygen and 2 hydrogens. And I have to say, if you are a scientist that studies water, it's about as, and you, it's a very contentious research area to be in because nobody ever agrees. So I thought, I thought religion was something that people debated a lot until I got started studying water, and it's as political as it gets. So this simple little molecule has created a lot of excitement in the community. So water has some very unique properties. Let's just go through some of those. It expands when it freezes, so it gets bigger when it freezes, which is why our pipes pop when they freeze. And I understand here it's more the issue that bridges freeze over, and so they isolate you to parts of town. So it can break pipes and also causes rocks to expand and explode. And what's so interesting to me is that its lower density results in it floating on top of the water. I mean, how many things do you know that when they go to the solid phase, actually float on top? Well, water does, and that's what makes it very unique. And so what that allows it to do then is insulate all the little creatures below that we and you want to all keep alive. And so it acts as both a surface layer as well as to insulate all the creatures that are below that these ice fishermen are trying to get at. But many of you have left that kind of world behind long ago when you moved here, and you'd prefer not to be reminded of it. Okay, so, but the other thing is it takes a lot of energy to heat up water. It takes a lot of energy to heat up water. A watch pot never boils, I guess, is a good example of that. And what I think is also just amazing is, that we can be here at 98.6, our bodies, and it stays in this, our temperature, as long as we're alive and breathing, stays in this very tight temperature range, right? It's very small, and that's all because of water. That's all because of water. I mean, your body is just constantly undergoing all kinds of chemical reactions all the time that put out heat and take up heat and blah, 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 and you get mad and, whatever. But it's that water that controls your temperature, and it's because it can take up so much heat before it changes its temperature. And of course that's why it's so important on the planet, because that's what keeps our planet at a livable temperature even with climate change. So it's, again, for this little tiny molecule, it has no parallel with regards to its ability to take up heat and other properties that it has. So why does it have these really special properties that you can't find in any other molecule at all, no matter how big? And so it's very special bonding, and I call that outside and inside bonding. And the outside bonding is what we call this, or the inside bonding is what we call this covalent bond. And what that means is there's a very strong bond between the hydrogen and the oxygen, and that's because it's not really a bar right here. It's a bunch of electrons buzzing around like flies over a cake in the summer. But what it is a very strong bond between here that holds the molecule together. It's just electrons buzzing around. And that's very strong. But there's also this much weaker outside bonding, and this outside bonding is what we call hydrogen bonding. And water likes to form these weak hydrogen bonds with other water molecules, which gives us its very special properties, which is why it can be a liquid at room temperature and so forth. Now these bonds, this isn't a formal bond, this is a weaker bond, but the difference in the scale of these bonds is like the difference between eating a Big Mac and a cracker. So there's a huge difference with regards to the strength of these two bonds, and yet this guy is the weaker, is the most important in many respects, because it's what pulls all these water molecules together to give it its very special properties. So we talk about water hydrogen bonding with other neighboring water molecules. And that's what, so a lot, when you hear about hydrogen bonding, you don't hear about this guy, you hear about neighbors interacting with one another. So, and it's because of this hydrogen bonding character that it's the only substance on Earth that at normal temperatures can exist as a liquid, solid, and gas. It's the only one. And a lot of this is because of this strange little weak bond, the cracker bond, the outside bond that causes it to be so special. So ice is a crystal of very different kinds, and it has the most number of hydrogen bonds. And so we generally think of strongest bond being the water bonds to 4 other water molecules, 4 neighbors. It's not monogamous. And water, and the liquid phase, though, it still has 4 other bonds with it, but it's much more random. The water molecules are moving a lot more. This is more the crystal structure. You can see the water's in here, and then they have these weak little bonds here. And then we get to the vapor phase, and that's where they break free. And they're able to move around, but they can still clump together at times in order to bond together. But it's the fact that we can have all these phases of water that makes it very special also. But the surface of water is also extraordinarily unique, and that's what I'm going to focus on tonight. And that is because the surface tension, the surface of the water, you know, you can float things on it. Bugs float on it, leaves float on it, and it's this high what we call surface tension. It's the energy that holds the surface together. It's almost like a piece of saran wrap over the water, because only it's extraordinarily thin. And it's that property that allows water to go from, you know, a river to the very, very top of a tree. You know, just think about how much work it takes to get water to the top of a tree that most of us can't climb. And so it's the special property of the high surface tension of water that gets it up there. And it also creates, what this is the end of a faucet, and there's supposed to be a drop that drops down, but the movie's not behaving. But the fact that, you know, in slow motion, you look at this water and it actually looks very viscous. You know, when it drops out, it's very viscous. And so it's this hydrogen bonding that causes this viscosity. So the questions we're going to, that we try to understand in our research is what kind of techniques can we develop to study this water surface? And that's what I'm going to tell you a little about, because it's pretty unique, and it's new methods. And how do these water molecules behave when they're just at this top layer? Why is this kind of saran wrap layer there? And more importantly, what happens when gases in the atmosphere, different chemicals in the atmosphere, come and land on that water surface? Do they sink? Do they swim? Or do they surf? And so there's our water molecule. And then do environmentally important molecules, as I just said, surf, sink, or swim on that water surface? And that's what we're after. So what tools do we use to study this very thin layer? Well, it isn't easy. What we want to get is just the guys right on top of here. We don't want them any deeper. We only want the few that are maybe 1 or 2 water molecule layers down there. And that's really, really hard to just get those guys and not the rest of the glass of water. We just want to know what's happening at that very, very top layer. And that's what's really challenging. And so our approach is to do a couple of different, take a couple of different approaches. And one is that we measure surface tension. And so I mentioned that surface tension for water is very high. But if you want to lower the surface tension, you throw just about anything on it and it'll lower it. So that's, of course, how soaps work, because their whole efficacy is because when the soaps go to the water surface, they lower the surface tension, and that makes basically breaks the surface tension. So one demo that I do in my one of my introductory chemistry classes is to take a cup of water. You can do this at home. Take a cup of water and fill it as high as you possibly can with water till it almost spills over. And if you look, you might have a little bit of a curve to it, but you get as much water as possible. And then you get a neighbor or whoever, your spouse, whoever, and you bet on how many pennies you can add to that cup before it goes over. That's your homework assignment. And if I were you, I would bet high, just as a clue, because it's amazing how that surface tension stays the way it is. But you got to be careful, because those pennies have to be really, really clean. Because you start doing this with the pennies, and you're gonna put in 1 penny. So we're talking real clean. So you might bake them in the oven for a little while, whatever. If you want to win the bet, it's all on how much you want to win the bet. But the point is that the surface tension is very strong, and you'll start to see it bubble over the top. Okay, so with surface tension, what we're doing is basically just measuring with a force. We're putting a little metal plate in here and pulling it up and see how much force it takes to come out of the water. What I love about surface tension measurements is as much the history as the information that we get. So surface tension and surface tension measurements, the first ones that were ever done, were by Agnes Pakal when she was a teenager, working in a kitchen, washing dishes. And she recognized that the surface of the water changed when she added soap to wash the dishes. And so she started playing with a button and a thread, and actually showed how that button on the surface of water changed as you changed the soap concentration. So she was the one that actually started the whole idea behind surface tension measurements as a teenager. And then and not a scientist, and then because at the time in Germany, women couldn't go into science to get any kind of advanced degrees, they sort of kept sneaking her in the back door. And then she coupled with some of the most famous physicists to actually get her work published. So it's just a remarkable study, but she did this all with a needle and thread, and to her we have an awful lot to thank. And then others, of course, took it beyond that, but just really remarkable. So when you look at your grandkids, at your kids as teenagers, you might have hope if they take up sewing. If they take up sewing. I could never get my sons to take up sewing. Okay, so, but that's the simple experiment to do. That doesn't cost very much. The harder part of the experiment is that we use very fancy lasers to do these experiments. And so for one of these experiments alone, we use very high-powered, very fast lasers, fast in terms of not running around, but they have very, very short pulses. And we reflect these off of the water surface, but they have the properties of the laser. You can't just go out and buy them. A lot of it you have to build. And so any particular any experiment is about two picnic tables worth of lasers with optics and so forth. And the worst thing you can ever do is walk into our laboratory and nudge any particular mirror, because the students will just kill you because they've spent months cleaning them. And so, and these are just a series of different optics that are used here. And so what we do is, and I'll talk a little bit about this nonlinear laser spectroscopy that we use. And it's kind of crazy because we have to put a lot of laser beams on the surface at once, and if we're really bad, we just boil water. So we have to be really careful, otherwise it's a very expensive coffee maker. And then we also do theoretical studies. So the experiments can only tell us so much. And then we have to do theoretical studies because they explain a lot of things that we don't really understand. Now, I've always been a skeptic of theoretical studies, I have to admit. And so the only way I can believe what we're doing theoretically is if theoretically they calculate something we see experimentally. So if we can calculate something that we see experimentally, then I feel more comfortable with going with the analysis that the theory shows us. So let me give you a little bit of the principles behind what we do. So if this is our poor little water molecule, vibrating as they do, and they've got these what we call OH bonds bouncing, and this is the strong bonds, the covalent. And if you were to try to figure out something about that molecule, what we commonly do in chemistry and in physics is we put light on that water molecule, and we look to see how much light you lose, what color of light you lose when you look at the light that comes out. Oop, my little R should be up with the detector. And so what you see is a chunk of the light comes out, which corresponds to energy of these guys bouncing around. Okay? So if we were to take some kind of a spectrum, what we say, of this water molecule, what kind of light is removed tells us how many other water molecules are bonded to it and a lot of other information. And so we end up with a spectrum that looks like this: how much light is absorbed versus the color of light. And so we would say, oh, that looks to me like a water molecule that's bonded to two other water molecules because it's of this frequency. So that frequency tells us something about the environment of the water molecule, or whether it's just by itself. Okay, now when we go to trying to study now a surface rather than sticking it through a glass of water, we're doing the same thing, and we're just taking light and reflecting it off the surface of water. And again, what you're going to do is some of the light will come out, and so you're going to say, oh, these water molecules at the surface, they are bonded to one or two other water molecules, and they have a spectrum that looks like this. So with traditional spectroscopy, the problem is that you think you're only getting the guys on top here, but actually this light penetrates 1,000 angstroms down, and you get a ton of water down here, not just the guys on top. So for example, when you're looking into a lake and you see yourself reflected, you think that your image is reflected, that you're seeing is really from the very top layer of water. But it's not. It's quite a bit deeper because the light penetrates that deeper. And so that's the challenge that we have in doing these experiments. If you've got just a few up here and then you're measuring all these guys down here, it's hard to distinguish the guys at the top from everybody else that's lower. And so that's why we have to get really fancy, and the way that we get fancy is that we now take two laser beams, and we have one that we call an infrared beam, tunable infrared beam, that corresponds to these water bonds. And then we also have what I say a fixed visible beam. It's basically a red beam. The color doesn't change, but it's hardly red. You can hardly see it. It's so deep red. And then the tunable infrared beam. And then what we do is if you're just getting these guys on the surface, they will produce a color that's the sum of these two colors. It's kind of a strange process. But the problem is that this red and this yellow light will also reflect off the surface just like normal. You know, you're looking in the river, the light, light goes in, comes back out. The problem is that this signal that comes out, that's the sum of these two frequencies that can only happen at the top layer, is about a billionth of an intensity of the reflected light. So it's tiny, tiny, tiny. And you have to work really, really hard to find it. But if you find it, it's going to tell you about the water molecules or whoever is at that very top layer. And so what we end up getting is, again, looking at intensity of the light coming out versus frequency. Now we're only going to measure the guys just on top. So if you haven't gotten anything else from this, it's just that you got to buy a whole bunch more lasers. And then on top of it, you can't see the beams. Your students can't see the laser beams because this red isn't really red. You can't see it. This infrared beam, you absolutely cannot see. And so talk about the emperor with no clothes, right? This is like the students are aligning the beams over at least 100 optics, so it's got to go bounce, 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 bounce through a whole bunch of different stuff, and they can't see the beams. Well, we have special goggles and so forth. You can try to pick it up. But then these beams only last about a trillionth of a second. So, right, so they're boom, 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 but they're only last a trillionth of a second, and then you can't see them, and then they have to hit the optics, and they have to hit the water surface at the same time in the same place. I have brilliant students, I tell you. And you know, they get their PhDs before 20 years is up, so that's good. That's good. Anyway, when we started with this technique about 15 years ago, there were very few people in it, and we were having to build our own lasers because you couldn't buy lasers, but now the field has progressed and there are a lot more people getting into it, so it's a bit easier. Okay, so what we're going to do then is get these funny spectra that tell us things about the different environments of the molecules. Okay, so this is just to give you an example of a spectrum, because we're going to use this when we talk a little bit further. All I want you to see in this spectrum is there's a big broad blob and there's a sharp peak. Okay? This corresponds to the these OH stretching modes of water at the top of a water. This is what the spectrum of your water looks like if it's clean, if the top layer of a glass of water that you're drinking. And these are just telling us what these OH stretching modes are like. And this guy right here is the most important because it's unusually sharp for water. And so we do a lot with this very sharp beam, this very sharp peak, because what it tells us is a significant number of water molecules in your glass of water have one bond sticking out here, just kind of hanging out here, and it's just hanging out there, and the other one's in water. Okay, so it's just hanging out there to say, hello, you know, whoever's up there, I'm here for you. And so that's why we like studying it, because it's the one that's most likely to interact with somebody else. And so this guy, if going up into the air, corresponds to that sharp guy. And that's what we call this free OH, because it's just hanging up there. And these guys down here are for water molecules on the surface of water that are more tightly bonded. So there might be with 2 or 3 other guys. So they're really having a party, and this one's sort of left by itself. Okay, and so this has to do with the fact, this is just to say that we do a lot of theory associated with it to calculate a spectrum that then, this is just a calculation of this spectrum that I showed you just a moment ago. What we do is, they're very detailed calculations that throw in a whole bunch of water into the computer, well, not really water into the computer, water models into the computer, and then run it to do the calculations. But it just helps us. So what have we learned? This is what the top layer of your water looks like. You got these guys here that are hanging out. This is a combination of both experiment and theory. So this top layer, this very top layer, very low density, very weak bonding, and they're highly oriented. The next layer, which is about 1 layer down, they're stronger bonding. They play around with maybe a couple other water molecules. And they also tend to be kind of oriented, even though they're bouncing around, they have a net orientation. Then you go down a little bit further, which we say 6 or 7 angstroms, so several molecular layers down. And then everything is random. So that first top layer, what I call that saran wrap region, actually has pretty weak bonding compared to bulk liquid. And so you can say, well, wait a minute, Geri, you just told me that the surface tension of water is very high, so everybody should be like hanging on to each other really tightly. And yet this shows you that the experiments and the calculations actually show you that it's actually quite weak. Well, it has a high surface tension, so it's hanging together like saran wrap, but it's also got to evaporate, right? So it's got to get out of there. And so that's what this top layer, and again, things are bouncing around a lot, but this top layer just facilitates water being able to leave. This is where all the action is, where you have stronger bonding and more cohesiveness between the water molecules, and that's what we believe is responsible for this higher surface tension. So why is it so important for us to be studying this from an environmental perspective? Well, because this water surface is the entryway for so much of the chemistry that happens on the planet, whether it be a lake in Oregon, Crater Lake, or whether it be clouds in the atmosphere, because the clouds clouds in the atmosphere are just a lot of frozen water with a lot of other stuff mixed in. They're little chemical factories up there. And we know very little about what happens in the chemistry of the atmosphere, because we used to think that all the chemistry in the atmosphere happened by 1 or 2 gas molecules kind of bouncing off of each other. But now we know that that's not the case, that it's actually little ice and particulates and aerosols in the atmosphere that's responsible for a lot of the chemistry. But we don't understand the chemistry at the surface of these particles. And so that's why this is important. And also, there's just a lot of stuff that goes into the atmosphere that's gaseous that then can react with a water surface. And so that's what our interest is. And near and dear to all of you is the fact that there's a real problem with regards to being able to separate oil from water. And it really relies on understanding how you separate, what the interactions between oil and water is when it spreads on a water surface, and how you might develop different products to clean it up in an environmentally safe manner. So I'm going to talk about some of these examples of what we've been doing recently. So the first example is something that's called a sulfur dioxide gas. It's a precursor to acid rain. And so sulfur dioxide is this little guy, SO2, and it's very abundant in the atmosphere, and it comes both from natural sources, but it also comes from dirty coal, right? So a lot of coal has sulfur in it, and the sulfur then burns and creates sulfur dioxide, which then goes into the atmosphere. And so that's why, and once it goes up into the atmosphere, it can then, what we say, oxidize and turn into sulfuric acid, which then rains down and kills trees, acidifies lakes, and so forth. So we have a lot of concern about sulfur dioxide because it can form what's called sulfuric acid and then rain back down again. And so our interest backs all the way up to trying to understand how sulfur dioxide, so and this forming of sulfuric acid happens on the edges of, is believed to happen on the edges of clouds, of ice particles in the clouds. Or it happens inside the cloud. And so our studies have really been to try to, from a very fundamental level, try to understand what happens when sulfur dioxide hits water. So it's, and then does it react, or what does it do? And so again, very fundamental study, but if you don't understand this first step, you can't go any further. And so what we try to do is to understand what happens when this SO2 gets close to a water surface. And so what happens as SO2 approaches the surface before it dives into sulfuric acid? What kind of interactions are there going on to help us understand what might be the next step? And so what role does water surface play in what we would call gaseous uptake, in this case sulfur dioxide? So this is your multiple choice exam now. I knew you didn't come for a multiple choice exam. So I'm going to give you 3 options, and this is going to make you listen if you want to give me the answer later. Okay. So is the sulfur dioxide, does that water act as a doorman to say, come on in, happy to have you, and then we'll oxidize you and send you off to ruin plants? Or is it a barrier, so SO2 comes down, bounces off? You know, does the doorman say, oh, just come on in? Is it a barrier to just bounce off? Or is it the temptress, which says, come on in? Now, for those of you that thinks that this is a sexist picture, I want to tell you that I went on the web to try to find the male equivalent of temptress. I tried really hard, and the only thing I could come up with was temptor. And the only pictures I could come up on the web was the devil. And so I apologize to anyone that takes offense to this picture, but you get the idea. It's to invite something into its haven. Okay, so now you gotta keep this in mind. Doorman, barrier, or temptress. So what we've learned from our experiments, when we do these experiments, is that we find out as there's evidence that SO2, once it gets to the surface, it actually forms a very weak bond with this guy that's hanging out there, that OH that's hanging out there. And so how do we see this experimentally? Well, the way we see this experimentally is this gray is that spectrum I showed you before with that very sharp peak, and that's pure water. And now, if I flow SO2 over that surface, or my students flow SO2 over it, you see this guy broadens. See, he's broader. And then you take the SO2 away, and it flips back. And so this tells us, because of the nature of the way this peak is, that actually SO2 comes onto the surface and hangs out there with this guy that's hanging out there. Okay? So, but that's all the experiments could tell us. It couldn't tell us anything more than that. It couldn't really answer the multiple choice question. It just said that it's there, and SO2 is there. And what's unique about this is no one has ever seen a gas form some kind of a surface complex with water before. Never been seen before. So that's what makes these studies unique. And so what we did was then calculations that then take an SO2 molecule and calculate what would happen if it got close to the surface of water. And so the next slide then is this movie. Okay, so all these are water molecules. These are just a few special ones just to say these are what they look like. And SO2 now is going to come down to the water. And I want you to keep an eye on those water molecules too, not just that big floppy SO2. Because that's the answer to the question. Okay? See? Going up to get it. And then we have to, the movie kind of, but what you see also for the chemists in the audience, you see actually that the sulfur goes down and stays highly oriented as it goes in, and then the movie stops. But so, doorman, barrier, or temptress? Temptress? Do we have a temptress? Temptress. Temptress. And in fact, when you do these calculations, what you find out is that that water actually goes up and gets it and pulls it back in. And so it's this attraction between the water and the SO2 that captures it there for a while. So the picture that I showed you before with SO2 going on to this guy hanging out here, that was really simple. And that's all that we could get out of the experiment. And it's only when we do these kind of calculations that it provides us the richness of an explanation. But it still ties in the fact that we could still see this guy hanging out here going after the SO2. So I used to not have any theoretical part of my research group. But now, if we don't do the two together, I'm always afraid that we're not getting the full picture. So that's the SO2 picture. Now, carbon dioxide, you may be a little more familiar with because you breathe it out all the time. And carbon dioxide, of course, is an important gas up there also. And so we did similar experiments with carbon dioxide to see if it would stop at the surface before it goes in to react. But actually what we found with CO2 is it just dives right in. It doesn't stop, it's just in there. And you know it's in there because that's why, you know, you put a glass of water next to your bed at night and in the morning it tastes really crappy. And that's because this CO2 goes into the water, turns into an acid, and what you're drinking is just carbonic acid. Or Coke without fuzz. So that's what makes this acidic, and so it tastes a little different. Or maybe your spouse dumped some stuff in there, I don't know. I don't know, I would believe that. My spouse would probably do that just for kicks. Or the dog would drink it while I was, yeah, one of the two. Okay, so the next little story is takes us a little bit further, and that's with acid rain. And the nitric acid that we have in the atmosphere comes a lot from stuff that comes out of the back end of the car. So there's a lot of NO compounds that come out. But we also get NO compounds from, as well as sulfur dioxide, from volcanoes, which I know you don't have many volcanoes here, but we have a lot up in the northwest. But this nitrogen oxide compounds, they go up into the atmosphere, and they also oxidize, and then they come down and make very acidic rain, can make very, very acidic rain. And so our interest is really to understand what happens when nitric acid is at the surface of water. Now, nitric acid, this kind of a compound here, which looks like a horse, but actually it's HNO3. And this guy right here isn't a gas, and so but it is going to be in water. It's going to be in the clouds, and so we're more interested in understanding if you've got a beaker of nitric acid, or you have a glass full of nitric acid, God forbid, because it's very acidic. And we know that nitric acid is a very, very strong acid. And nitric acid is a very strong acid, and the way that we look at it is this hydrogen pops off really easily. And so a very strong acid has a hydrogen on it that pops off very easily. And so it's very caustic when this guy comes off, and very reactive when that guy comes off. And so our interest is to understand if nitric acid first does nitric acid sit at the surface, because you never know, it can be hanging around inside swimming, but it may not be on the top surfing. And if it is there, is it a strong acid at the top or not? Because if those clouds are going to react with all kinds of stuff out there, and the inside is a very acidic soup, maybe the outside isn't. And so that's what we wanted to understand, is what nitric acid was like at the surface of a solution of nitric acid, again, as a model system for understanding what goes on in clouds. And here, just showing that the hydrogen comes off. Okay, so Now, for those of you, I have to entertain those people from chemistry department that understand spectroscopy. So this is their slide. Okay, so when we do these laser experiments, which these are extraordinary, these are even more difficult than the water ones because the signal's low, you basically find out that this nitric acid guy right here, from the experiment, it says we see a peak around this number right here, but they're nitric acid molecules that actually are hanging out of the water, and they've only got one water molecule bound to them. So nitric acid is actually hanging out there. That's in, and the rest is full of nitric acid too. But then we find another guy at another peak, and that corresponds to a nitric acid that only has one oxygen going up, but it's bound a little bit tighter to other water guys. So that's what the experiments were telling us. We looked in the literature to find out what these kind of numbers correspond to. And so what we found is, yes, indeed, nitric acid, undissociated with its proton there, is on the surface of water. Now remember I said that when it's dissociated, that's when it gets really bad. And we never found the dissociated nitric acid. We could only find the protonated. The only ones we could find was with the hydrogen, not without the hydrogen. So then we went to do the simulations, and so just to get your eye set on this, we wanted to see if the simulations agreed with what those pictures I just drew, that nitric acid does bond to other water molecules and very weakly. And so this is a nitric acid, this is the hydrogen going back. These are just some water molecules. The blue ones are water molecules too, but these are the ones that are involved in bonding, and this is what the calculations tell us. One bond. Whoops, two bonds. And then goes back to one bond. So never more than two, generally one. And the longer this guy gets, the longer this white dot gets, it means the weaker and weaker bonding interaction. So we discovered for the first time that nitric acid sits on the top of a water surface. Everyone always thought it was dissociated, but it's actually protonated. But even more important is the fact that it's the question of how does this weak bonding affect the acidity. And so what we've found from that is that when nitric acid, so why does this guy ever want to lose its proton at all? I mean, why give it up? And it will give it up when there's a lot of water around, saying, I'd make you a lot happier if you were an ion and the hydrogen came off as an ion. So, you know, get with the program and we'll dance, okay? When there's not a lot of water around the nitric acid, it's not about to give up its hydrogen because there are not a lot of others to dance with, if I can say it that way. And so when nitric acid is at the surface, there's just not enough water to pull that hydrogen off. And so it stays as a very strong acid as a very weak acid at the surface because it doesn't want to give its hydrogen up. Remember, it's stronger if it gives its hydrogen up. And so what we've discovered, which was very unexpected, was actually nitric acid at the surface is not nearly as reactive as it is when stuff goes into the bulk. Okay, so the last study is just summarizing a little bit of the work that we've done of water covered with oil. And as we know, I just mentioned that soaps and detergents, they're important, but they're particularly important at an interface where water and oil are involved because they tend to work in your laundry detergent because what these guys do is they go directly to the point at which the oil meets the water and they cause it to break up. And so what we'd like to be able to do is just some fundamental understanding of how you might be able to come up with new compounds to clean up oil spills. But also, this oil-water interface is a unique place for making materials. So polymers, there's a possibility of making polymers there, but also just interesting properties. So where the oil meets the water is really interesting. And it's an area of research that's been very little has been done on this on a molecular level. And so I'm just going to simply talk about what we've learned about that interface and some of the applications. I talked about this in chemistry department today. So we normally think that when oil comes next to water, they don't like each other, right? Oil and water are what we say is immiscible, but they really don't like each other at all. And so for a long time, people believed that when you put oil on top of water, there was a vacuum layer which had nothing in it. So a region, quite a thick region, where there was nobody there, because that was like the battlegrounds between water and oil. And so what we've discovered is actually that picture is completely inaccurate. And in fact, what happens when oil is on water is the following. is that you've got these water molecules like I showed you before, and like at the air-water interface, there are some guys that straddle the interface. So one OH going into the water and one OH going into the oil. And so at that interface, they actually interact with one another. And we actually find that this guy, I'm going up and down, that this guy actually bonds to the oil. And that leads to special properties that draw a lot of other stuff there, like ions and so forth. And so for those of you that may know some biology, this oil-water interface is a model for anything that's water next to a hydrophobic surface, such as a membrane, water next to membranes, and you can have ion transport across those membranes. And so this really sets up the science behind why you actually can get these ions drawn in across a membrane. But those are details. But the point is that this interface right here is really unique in the area of surface science that we work in, because it has this aligned water molecules that then set up a very attractive place for a lot of stuff to go. But it's also a very narrow region. So this kind of an effect only is a few water molecules down into the liquid. So what we've been doing in recent years is, once we've discovered the properties of how water molecules and oil molecules align there, what we've been doing is to try to study what soap molecules look like when they go there. Okay? So whether it's soap from your toothpaste or your laundry detergent, all of those are what we call soaps or surfactants. And the reason these guys are effective is because they generally have, and why they like to go to the interface is because they generally have a water-liking chunk, which is oftentimes a polar head group, what we call it. And this part likes to be in the water. And then they got these long, oily, wormy tails, and those wormy tails like to be in the oil. And so soap molecules are really schizophrenic because they can't quite decide, you know, I don't want to be in the water. No, I want to be in the oil. And so this kind of tug of war as to whether they'll go there or not. But once they go there, they're very happy here, because as long as this guy ignores the rest of the tail, it's fine. And so what we try to do is understand when they go there, how they orient, how they align, so we can understand better what kind of a structure you want to put in these purple balls or these tails in order to make them more effective as a soap. So we don't go making soaps, but what we do is to try to understand the properties that someone else could use to design a new soap or more effective detergent. So these guys are really happy. They love to be at the interface. They like to stay there. And of course, that's how your laundry detergent works, in that you throw in, you've got a shirt there. It's got some oily spot on it, and what these soap molecules do is you put the water in. Soap molecules do is they go in there and they get together in the oil, and then they decide it's a little too crowded here. Let's bust this place up, and so the oil busts up, and you get emulsions forming, and all the action happens. But they're very happy there until too many get close to each other. Okay, so what this leads to is, the more guys you get there, the lower the surface tension is, and the ability for it to cause an oil to be dispersed, whether it be in your clothes or anything else. And so a lot of the common dispersants that you have when you're cleaning up an oil spill are these kind of surfactants, only oftentimes a lot more complex and not nearly as biologically friendly, environmentally friendly. So what we've learned is that oftentimes, though, some of the guys, they have a mind of their own, and they aren't effective as a soap, because what I showed you in this slide was, if they're a really good soap, we've learned that their tails lined up really nicely. And all the tails are interacting with one another because they're also really oily. But sometimes there are soaps that don't like each other very much, and so they get really disoriented, and everything's kind of random, and so then the surface tension doesn't lower, so they're not as effective as a soap. So those are the kind of things that we study. And so we also study some polymers, and in particular what are called polyelectrolytes, and these are the more advanced kind of dispersants that you might use. But polyelectrolytes are used a lot, and what they are is just this long chain of carbons, and then they've got these little charged groups on them, like was on the surfactant, the soap I showed you before. And these little charged groups are like light bulbs on a Christmas string. And so these guys are really important in a lot of different applications, whether it be oil drilling. They're also good models for DNA and understanding assembly, and they're also important for understanding more biological systems associated with soils. And so our interest was to try to understand how these polymers might go to an interface. Do they string out, or do they just clump up? Because if these guys are thrown into water, they tend to like to clump up a lot. And so we try to understand how they might go to that junction, what conditions there are most favorable for that going to that junction, and how that would affect then lowering the surface tension. Well, what we found is just an amazing discovery, and that is that, yes, they do go to the surface, but what happens is that you get only one layer that goes down nicely ordered, just one, very thin, 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 thin layer. And the reason for that is because I told you there's this strange orientation of water that likes to draw things in. And the rest of the polymers then go down completely disordered. So you get this nice layer that goes down and then a whole bunch that clump up together. And that's very different and very interesting because it tells us more about how we should think about how a polyelectrolyte might be effective in some type of breaking up some kind of oil. And so what we're doing now in the next phase of these studies is to go beyond these studies, and polyelectrolytes are assumed to be really important as surfactants, but what they're finding is that actually if you dump in some soap with the polymers, just the simple surfactants I showed you before, that they're even more effective. So what we're doing is studying how now different types of soap molecules might go there and how they interact with the polymers and why they're so much more effective in breaking up oil and water. So that's the next phase of these studies. And the last part is to understand taking little tiny nanoparticles that have the polymers coated around them, and then studying how they go to that interface. And what we're finding is actually they go to the interface very nicely too, but only the first layer. And once they go there, it takes some jostling around until they're settled into a stable configuration. So these in particular are looked at as the more advanced stage of coming up with new dispersants because they have the potential to be even more environmentally friendly. So that's my talk tonight. And my final quote is, if there's magic on the planet, it is contained in water, but I'd like to modify that. It is contained on water. But the real credit goes to my gang back home. And this is a series of pictures of them over the years, not the same ones over the years. But this is we have lots of traditions from dressing up every year for Halloween. We also have a tradition, this is of pieing each other for various things, like you forget to tell someone your birthday, so you get a pie in the face. But it's a tradition in my laboratory to do this, especially if you pass your PhD exams. And it actually started because a group of mine in my first years at Oregon decided that they were going to take up a hobby, and that hobby was going to be skydiving, which is not a good idea in Oregon where we have a lot of clouds, but they took up skydiving. And when you did your 100th jump, you got pied. And that eventually went into the laboratory because that was about the time I got tenure, and so they decided to pie me even though I'd never jumped out of an airplane or never planned to. And so it's continued over the years. This is my Floridian, Adam Hopkins. I've had a number of students from Florida over the years that I've enjoyed immensely. But if it weren't for them, I wouldn't be doing this because they are everything to me. Being with them every day that I'm home and working with them, nothing could be a better job than that. So thank you all very much for coming out tonight, and I'd welcome any questions at all that you have. Question up here? Question over there?
Thanks. Yeah, you talked about sulfur dioxide and the nitrogen oxides as combustion products in the atmosphere. I'm curious about how do they get oxidized to sulfates and nitrates? Is that in water, or is it atmospheric oxygen, or both? Or?
It's ozone, a lot of the ozone in the clouds, but also they don't know if the ozone, for example, makes it to the top of the surface. And there can be some gaseous oxidation to make them into those acids, but the current thinking now is it's happened either on the surface of clouds or inside the clouds, but it's largely from ozone. And also from, as you get to the higher atmospheric areas, you get more of the radicals that can bounce off them. But it's largely ozone in the clouds. It's a good question. Mm-hmm.
Thank you for a wonderful lecture. You mentioned the sulfur dioxide, the carbon dioxide, and nitrogen oxide being the water, the oceans were a tempest for those gases. And in that the Earth's surface is 70% water, couldn't God or nature have designed the ocean to take those gases and modify them? Or is that possible? And are these gases toxic to the ocean, or does the ocean neutralize them?
That's a good question. Actually, a lot of yes, they certainly go into oceans, and yes, we are very lucky that we have so much water on the planet, as much for temperature control as anything else. Are they, once they go in and they acidify, well, carbon dioxide tends to be what we call a buffer. And so it tends to kind of, it protects you for a little while. But if it gets too acidic, then it plummets. So it kind of balances a bit, but once you fall off and go a lot more acidic, it really goes down a lot. And so there's actually a lot of concern right now about the increased carbon dioxide in the atmosphere is actually causing more acidification of the oceans. And so there's certainly parts off of the Oregon coast where we have dead regions where everything is dead. And so they're trying to understand what's causing this extreme acidification of the water off the coast, west coast. And some of it, people believe, is due to carbon dioxide, heavy concentrations of carbon dioxide, which of course are coming for us. A lot of it's coming over from China and so forth because of we get a lot of pollutants from there. And some of it is just, some of it's natural, but some of it is having to do with a lot of these other compounds out there. But I think the verdict is uncertain right now as how much is due to carbon dioxide, but it's the most likely culprit because we've increased the carbon dioxide concentration in the atmosphere so much. It's a good question. I think there was some hands up here too. Yeah. And then I also see back there. These are great questions.
Thank you very much. You particularly gave me a sense of gratification. I was a part of the team that first did laser spectroscopy.
Yeah, you can pronounce it.
Because before then, we weren't able to get rid of the ion bands, the bands that generated the radiation. So that's fun to see what you've done with it. I also work for Procter & Gamble, and we have a product called Dawn. I didn't work for that area, but Dawn is much, much better than all other surfactants for a lot of things. There's not just surfactants and surfactants.
Right. So I don't know what's in Dawn, but it is true. It's much more gentler. It's much gentler. And I have a sense of, so for example, if you take the soap that's in your toothpaste and you take the soap that's in your shampoo, there's like one atom in that molecule that's different. And yet you would never brush your teeth with your shampoo, right? Or wash your hair with toothpaste. And yet, molecularly, they're, if you just kind of look back and forth, they'd look identical. But it's when you start doing these kind of studies that you see that actually their behavior can be very different only if there's just one atom that's different. Amazing. Yeah, it is amazing.
I do know that Procter & Gamble has a lot of scientists, have billions and billions of dollars of research to make these things happen. Perhaps they're another source of collaboration for you.
Yeah, that's right. And it's a hot, right? Because you got surfactants in your motor oil, you got it in just about everything. I think we have a question back here. We'll give you your exercise.
Thanks for the presentation. I was wondering, when you're doing your experiments and you're passing SO2 or nitric acid gas, I would assume, over the surface. SO2 gas. Are you doing that in a Faraday cage, and are you accounting for electrostatic effects at surfaces? And if you might comment on that. I have an interest in metal chelation at mucus layers on alveoli and air breathers and on gill surfaces. And I believe there's a bioelectric field that influences the attraction that goes on at those interfaces. So I was just curious if you had addressed any kind of electrostatic issues or dielectric issues.
Well, the dielectric issues, we're doing shop talk now. The dielectric issues are a big deal because we try to understand how the dielectric of the material of the water versus the oil might affect it, and there's some nuances associated with that. But as far as a Faraday cage, we haven't found that we've needed to do that because we're working with, the kinds of fields that we're working with are so tiny because they're in such a very, because of the region that we're working in, and that we haven't felt that it's been that important. More important has been, which is a really difficult part of our experiments, is to get everything clean enough to study it. So we're talking ultra pure water that then you dope. Because if you were to just take tap water, it's disgusting when you look at it from this laser. I mean, I would drink it just fine, but it's the level of sensitivity that we have to these experiments, that if you want to see a war, you just walk into my lab and take somebody's beaker and do anything with it, breathe on it, you know, put anything in it, because it's class warfare to, once you get your beakers clean and all your glassware clean, that's the biggest issue that we have, because that can put ions in and so forth.
So you haven't seen any effects on liquid surfaces that are like in a beaker or something?
No.
Something to that effect?
No,
So have you done any studies with aerosols, water aerosols, and interacting with molecules?
Not in aerosols in the atmosphere, no. But what we are doing is experiments where, which is sort of in that direction. We're taking these experiments from where we're just looking at a planar surface, and we're taking that oil and water and shaking it up, and then looking at the surface of the little tiny particles of oil that are dispersed in the water. And so that gets us closer to sort of the aerosol direction, where you're studying little tiny beads, and it's absorption on little tiny beads as opposed to just a flat surface. And that's as close as we get. There was another question. A couple here. We'll come back. Okay.
Fun to be in your class for a night. Thank you. I was interested in your bio mentioned implications for energy production. And it seemed like I remember a couple of years ago being in one of the lectures here where a person was talking about possible sources of energy production for the world with population exploding and so on. And they went through and said it couldn't be in oil, and it couldn't be in coal, and it couldn't be in nuclear plants because you just have to continually build them because they die out after 30 years. And it couldn't be in wind, and it couldn't be in solar, but it could be in water. It seemed like I remember them saying even that they were working on like a home-based system where each home, I mean, just a cup of water out of your swimming pool would be enough, could generate enough power so that we would all fill up our cars with the power from home and would be off the grid and so on. What, where have things gone from there?
Okay, so, well, the kind of research that we do actually is a whole other project I didn't talk about, which is solar energy associated. But if there's anything that I see as promising is that it's not, it's water, but it's more associated with hydrogen. And that is hydrogen storage. And so it's not really like a photovoltaic cell where you put in light and you get electricity out. Here's the deal. You've got your solar panels on your roof, and it's collecting all of this electricity. And it's storing it up when it's nice and sunny. And then it gets nighttime and you're not producing electricity. So you have great electricity in the daytime, but then, you know, it's not very well. So what are you going to store that electricity in? And so the push is to store that in hydrogen. And so when you hear people talking about hydrogen-fueled cars, what they're talking about is hydrogen as a storage medium. And that's coupled then with water in terms of being able to produce the hydrogen and so forth. But the idea is that you would have this little little generator next to your house. So the solar energy produces the electricity, and then it converts the water into hydrogen gas. And then the hydrogen then you can get the electricity back out again if you do the right reactivity. So it's looked at as a storage medium. And so for a number of years, I was on the Secretary of Energy's panel on hydrogen and hydrogen storage. And there were all the heads of car companies on it. And they would love to see us go to where we're just putting hydrogen gas into our cars as opposed to oil and gas, because it's very clean, because then you just end up with water once burns and so forth. But, you know, everybody remembers the Hindenburg, you know, and so, or at least us older folks do. And so there's a real tendency for people to be afraid of having hydrogen around, when actually it can be controlled in a good manner. And that's what we're talking about with a lot of these battery-associated is as a storage medium. And then there's water associated with it because it's a cycle between water and hydrogen gas. So it's an interesting technology and one that may be promising for a very long time.
I've got a fairly simple question. You spoke a lot about surfactants and living on the Gulf Coast with oil spills and all that. And I think of just dispersing all this stuff all throughout. Is there attractants? Maybe you can attract the oil and then lift it out so it doesn't just go all over the place.
So that's a point of, you know, I said these nanoparticles that we're trying to study. The idea behind those is that you can actually use these to encapsulate the oil, and even some of the surfactants to be able to encapsulate the oil, remove it from the water, and then dump the oil, and then these guys come back and you can put them back into the water to do more cleaning. So it's reversible. So unlike the dispersants now, which, yeah, they disperse it, but then they're still in the water too, and you're stuck with them. This idea for black water, gray water cleaning on a ship is that way you can just recycle these dispersants, but actually what they're doing is collecting it all together and then dumping and then coming back and collecting it. That's conceptually what the idea is behind those. And there are a number of people working on that, and I think that's going to look promising for gray water and black water applications. I don't know how promising it's going to be in some type of an ocean cleanup. But you know, I'm way up in the Northwest, and we have our share of problems, but it just broke all of our hearts when this happened down here, because water is really special, as special to us as it is to you guys. Yeah, it's really horrible travesty. Great, thank you.